lab, and he will be giving some of his recent work at Berkeley. Yeah. So please go ahead, Jan.
Hello, everybody. I apologize. I could not be in person. I will be presenting work on first principle crosstalk dynamic learning through Hamiltonian, and this is experimental work, which I am a researcher at Berkeley National Lab. This work has been supported by the Office of Advanced Science and Research, as well as US Department of Energy. The paper which I will be presenting today has been already posted on the archive, and I believe, so here's a whole author list, and I believe Elon, Neil, and Gang are somewhere in the audience, so please raise your hand. I'm presenting our common work here. So now let's move to the actual talk. So I will first discuss what is the crosstalk in the quantum system. Next, how are we modeling with the Hamiltonian? I will give a brief overview of the advanced quantum testbed at the Berkeley, as well as the controller which we are using for the taking all the data. And finally, I will go to the main part where I will show that we have successfully measured the crosstalk in the device and verified the model is reasonable. And I will conclude with a summary. So let's start with the crosstalk. So in general, it's unwanted coupling between different signal paths. And in the context of the quantum processor, it could be also a quantum coupling through the entanglement. So here you see on the right-hand side a photography of the chip, which very similar to the one which I have used in the experiments. And it contains 8 qubits. I highlighted 3 of them in different colors. And the question we want to ask is, if I drive the green qubit, and at the same time send the electrical pulse to drive another qubit, let's say the red one, how the behavior of the green qubit will get distorted, how much different gate I will achieve because I also want to simultaneously drive a different qubit. And of course, one naturally assumes that the crosstalk will be strong between the qubits which have a couplers between them. So I draw the diagram on the bottom, which shows the couplers. But in reality, there is much more interaction going in the chip. So if one models how the wave propagates inside the package, here you see some mesh analysis of chip under design, one can find out that one can expect that the qubits farther away from each other, not coupled to each other, will also experience some kind of a crosstalk. So of course, there are many models how to describe it, and then you can optimize the design of the chip to minimize it. But in reality, there is always some residual crosstalk among the different qubits, which we want to at least know and measure experimentally before we can correct for this. So how do we approach this problem? It is of measuring crosstalk and modeling crosstalk. So we assume for now it's a linear combination of the amplitudes which lead to the crosstalk. So it's very similar to the combiner, which probably some of you know from the electrical signal propagation. So in this case, we want to drive a qubit Q1 with some signal from FPGA, and this signal is delivered by some wire. And the question is now, if we at the same time send a signal to a different wire, let's call it D2, how much this signal will bounce around the box and between the different electrical elements in the qubit, and it would distort the qubit 1. So we decided that it's enough to describe this interference with the 3 parameters, namely the strength of the crosstalk, the relative phase of the crosstalk, because we will be adding amplitudes as a function of time. And of course, this implies that we also need to know the relative delays in the cables, which won't be identical to the precision which we need while we are driving qubits at, let's say, 10 or 20 gigahertz. So in general, one can expect that the crosstalk model for a fully connected, it will be a fully connected graph, and it will be directional graph because the crosstalk does not need to be symmetric. And here I'm just showing example of one result, which I will discuss in more details later, that for the qubit number 2, we see that it's stronger coupled to the qubit number, to the signal delivered to drive line 1, 6, 5, 4, and 3, but the strength is not the same. So this is kind of information you want to extract from the chip using measurements. And the way we approach it theoretically, we define the Hamiltonian for every qubit, which is indexed with J. And this Hamiltonian has the main term, which is when I drive the qubit with some pulse. And this is, you see a circuit here on the right-hand side, where the qubit A is driven with the Rabi pulse. And for this particular protocol, we have chosen the rotation angle to be 2.5 pi. So it means we want to rotate the qubits full around the Bloch sphere and additionally 90 degrees. So if we measure this kind of pulse with in the Z basis, the average value will be 0. So without presence of the noise, we should get expectation value of 0. But now we add a second drive on a different channel, and this drive will have exactly the same Rabi pulse with the same frequency, but we insert some delay. So this is the protocol on experimental side. And now mathematically, it was equivalent to obtaining this kind of equation 3 in the amplitude of the signal. And now the goal is to find the coefficient tjk and theta jk from experiment by running all possible pairs and measuring the distribution of expectation value on the target qubit as a function of the delay delta phi of the signal driven on the other qubit. To perform this experiment, we are using advanced quantum testbed at LBL. And on the schematic level, the system is kind of standard dilution fridge driving and measuring. So we have a controller of the quantum device, which drives pulses, and they need to pass through several layers of cooling until they get to the chip, where we drive the qubits, and then we measure some of them, and then the signal needs to go back and be recorded and passed to a classical computer where I can sit and do the analysis. On the right-hand side, you see that how the actual hardware looks like. So the white dilution fridge is quite large, it's size of me. And on the side, you see racks with the controller where the hardware and software controlling the device is sitting. The chip itself is at the very bottom of those cylinders. It's quite small. It's like 1 centimeter about in size. So this is the hardware setup, and the software which I'm using is called Cubic. It's open software developed mainly by Gang and Elon, which I hope, just raise your hand again, guys, if you're in the room. So this software, I believe there are separate talks about this. I will only mention that it allows for parallel, it allows for controlling more than 8 qubits, because we can connect multiple of those devices together so they can work in parallel. And this is very flexible software. So now let's go to the experiments. So as I mentioned earlier, the primary experiment to measure the crosstalk strength and phase for the pair of channels has this kind of chip, this kind of quantum circuit. And on the right-hand side, one see well, let's go to the left-hand side. So with this experimental setup, we always measure the expectation value of the qubit A as a function of the delay delta phi. And the bottom plot shows here the case which there is almost no crosstalk. So the points are from the measurement, and without any crosstalk, we will see just a flat line. There is a small crosstalk from the qubit number 4, which is shown on the top right. And this causes a very small distortion. Whereas if we choose as qubit B a different qubit, let's say 0, we will get a top plot where the distribution is very significantly distorted. So now the challenge is to fit the model, the Hamiltonian model of this signal, which has shown the formula on the right, and has three parameters: the beta AB, which is a crosstalk strength, and the theta AB, which is a crosstalk phase. So we allow to vary only these two parameters, and we want to get as good fits as possible. And as demonstrated on the left-hand side, we get a very good fitting for all the cases which I'm showing you here. And you need to believe me that this is true also for the remaining 8 times 7 by 2. So 50 other combinations which we have measured. So we determined the crosstalk parameters beta AB and theta AB for all possible pairs. And now this constitutes the model of the crosstalk. So this is the success which we declare. But of course, you can ask, well, how do you know it's right? So in order to test this model of the crosstalk, we conduct. Okay, let's just show you the final result. So this is the crosstalk determined for the whole chip. And the thickness of the arrow denotes the strength of the crosstalk. So as you can see, the crosstalk is mainly along the coupling lines, which are shown as a small diagram on the right. But there are also strong couplings between the qubits which don't have a coupler. So these are the unwanted terms, and this kind of measurement provides a feedback to the manufacturing process of the chip. And perhaps in the next iteration, the process will be changed to reduce those unwanted crosstalk terms. So now I come, the conclusion from this measurement is that the strength of the crosstalk varies between the qubits significantly. You see some of the lines are thick, some are not existing. The crosstalk is not symmetric, as you see, between 7 and 6 is strong, and between 6 and 7 is much weaker. The head of arrows denote the directionality. And as I mentioned, mostly the qubits which have the couplers have also exhibit the crosstalk. So now let's go to the next stage, which is verification of the crosstalk model. So to verify it, we run experiments where we send signals to 3 driving lines. So it's kind of extension of the previous experiment. But this time, and so we again measure only 1 qubit, but this time we want to predict what will be the signal measured on this qubit. And again, reminder, if there would be no crosstalk, the signal will be just flat line. So all variation which you see on the, let's say, on the figure A here, is coming just because driving qubit 1 and qubit 6 concurrently with the qubit 0 causes the distortion. They are humongous. And our model is able to predict them very well. So for this case, the chi-square per degree of freedom is just 2.2. And again, for the second combination of the qubits, which I'm showing here, the prediction is very good. For the third plot, figure C, the chi-square is not great. It's 12 per degree of freedom, but we can find why is it. So there is a portion of the varied phase of the driving pulse where the predictions are giving the expectation value to be -1, which is the maximal possible, yet the actual qubits never reach this position. So this is most likely the case where either the calibration deteriorated or there is some other errors in the qubit itself. So it cannot reach the bottom portion of the Bloch sphere. So for the majority of the distribution, the prediction is very good. So just to up the challenge, we repeat this kind of measurement again, but now with driving 4 qubits and asking how well we can predict the crosstalk for 4 qubits. And the answer is very similar. So for majority of the choices of 1 qubit being target qubit and additional 3 qubits being subject to the noise, we can predict it very well. In some cases, as shown on the bottom, we don't have a perfect prediction, but it's again the case when the crosstalk predicted would drive the qubit to the maximum, either on the top of the Bloch sphere or on the bottom, and the actual qubit cannot reach the state. So that's why the chi-square is not that high. So this concludes the talk. To summarize, theoretical characterization of the crosstalk for the QPUs is a complex problem. We have built a Hamiltonian-based linear model of the crosstalk And this model has been trained on the data, experimental data collected using the chip at the AQT, using the qubit controller, measuring of the crosstalk for all qubit pair is sufficient to predict what will be the distortion if we drive 3 or 4 qubits. We have shown this experimentally. And as a future direction, we are hoping that this learned crosstalk model will allow for the correction of the driving pulses in the present if are multiple driving pulses, and this should lead to the higher fidelity of the quantum gates executed on the NISQ devices. So the QR code for the paper is provided, and I also encourage you to hear Gang's keynote talk at 2 p.m. where he will talk more about the cubic and how it works. Thank you.
Thank you very much, Aaron. We have time for 1 or 2 questions. I do have a question myself. What are the insights you can pass for control system developers or error correction developers based on the crosstalk analysis? Like, are there any insights for error correction?
So I think that this talk is kind of living in a different Riemann plane. So here we are trying to correct errors for the gates, and for the error correction, you are expecting that the gates are very good. So the errors which I was showing where the correction is like 100%, it means that the gate is in the presence of crosstalk is very bad. And for the like analysis which was presented before my talk, you are expecting that the starting error for the gate is like 10 to minus 4. So I think I am kind of still grounded in the NISQ era, and the error correction analysis or work which you were discussing before is for the devices which are way, way better in quality on the hardware level.
Thank you. Okay, we'll move to our next speaker, Long Nguyen, and he's from the Computation Research Division in Lawrence Berkeley National University.
You just lock your computer in, or you have to join Zoom. Okay.